Hi everyone, I'm Yeonhee Park. It is my pleasure to present one of my research today. This is about Bayesian simultaneous partial envelope model with application to imaging genetic analysis. This is a joint work with Yanbo Shen and Chumin Zhang from UW Medicine and Saptarsi Chakravarti from University of Buffalo. I will provide motivation and review of envelope models first, and then I will introduce a new model based on simultaneous partial envelope model. And I will wrap up with the concluding remarks. So the motivation is the study of Alzheimer's disease neuroimaging initiative, shortened to ADNI. ADNI study has collected the imaging genetic data in order to advance the discovery in detection, invention, prevention, as well as the treatments of Alzheimer's disease. Imaging genetic is an emergent transdisciplinary research field to evaluate the association between genetic variation and imaging measures. The challenging problem here is that the number of imaging phenotypes and genetic markers are relatively high. But this is not a surprising problem nowadays, since we live in an era of big data. Similar to a recent large-scale imaging study, we were interested in characterizing the genetic influence on Alzheimer's disease candidate genes on the brain phenotypes of regions of interest, ROI. Brain measures usually show the strong bilateral correlation and tiny differences between hemispheres, so it is reasonable to suspect some linear combinations of brain measures carry no information to the regression. Also, some linear combinations of snaps might not be crucial to the imaging genetics relation either. So envelope models aiming at learning those redundant linear combinations of responses or predictors will be helpful to remove them in the regression for better estimation efficiency and prediction. So let me review the envelope models. Suppose that we have multiple predictors and multiple responses. Then we can consider the multivariate linear regression expressed in this equation, regressing R-dimensional response vector on P-dimensional predictor vector X. Here, epsilon indicates the error with mean zero and covariance matrix sigma y given X. Then under the standard model, we estimate the regression coefficient beta by regressing each element of y on predictor x, and then collect the estimates all together. So this standard model approach ignores the relations among the response variables. To address the issue, envelope model was introduced in 2010 by Cook and his colleagues. The idea is to partition the response vector y into material part and immaterial part. We call the linear combination of y the material part of y if the distribution of the material part changes with the predictors. Otherwise, it is the immaterial part of y. Specifically, let S be the subspace of the R-dimensional real-valued space. PS indicate the orthogonal basis of the space S, and QS is the orthogonal basis of the complement of S. You could imagine PS as the projection matrix and QS is the identity matrix minus the projection matrix. Then Py and Qi satisfying the two conditions in equation 2 are material part and immaterial part of Y. The first condition says that the distribution of immaterial part Qy does not depend on the predictors X. And the second condition says that given predictors, material part Py and immaterial part Qy are not correlated. The two conditions can be rewritten as the parameters beta and sigma y given x. Here, let big B be the spanned space by the regression coefficient beta. Then the first conditions will be the spanned space by beta belongs to the subspace S. It means that immaterial part, which is the orthogonal to the space S, which is the basis for the complement of S, so the immaterial part will not provide any information for estimating beta. And the second condition, the independence, provide us such a decomposition of the variance sigma with the variability due to material part Py and variability due to immaterial part Qy. Of note, with such a special structure of sigma, Conway says that the space S is a reducing subspace of sigma y given x. And Cook and his colleagues define the sigma envelope of the spanned space by beta as the smallest reducing subspace of covariance containing the spanned space by beta. So they say that standard model with two conditions expressed in the equation 3 is called the envelope model. Let U denote the dimension of the envelope. If the value of U is the same as the R, number of response, then the envelope space is the same as the R-dimensional response space, and envelope model degenerate to the standard model. For the fixed dimension U, R times U matrix gamma denotes the orthogonal basis of the envelope space, and gamma 0 indicates its completion. Then we will have the coordinate form of the envelope model. Y is mu plus gamma eta x plus epsilon. So now beta is replaced by the function of the basis gamma for some matrix eta. So eta carries the coordinate of the beta with respect to the basis gamma. Also, sigma y given x is decomposed into two variability written as omega and omega 0, and omega 0 will carry the coordinate of sigma with respect to gamma and gamma 0. So Cook and his colleagues shows that envelope estimator of beta is more efficient than, or at least as efficient as, the standard estimator. And the efficiency gains can be substantial when the magnitude of the variability due to material part is less than the magnitude of variability due to immaterial part. Here, magnitude is measured by spectral norm. So let's see the graphical illustration to understand the envelope model well. So left and right panel shows the analysis using the standard model and envelope model respectively. This illustration considers the two population mean comparison. So we have two populations following the normal distribution having the equal variance but different mean. So we are interested in mu1 minus mu2 in this problem. Such a two population mean difference problem can be considered in the context of linear regression, regressing y on the binary predictor indicating the group membership. So here, then the parameter of the interest beta is mu1 minus mu2. And this directional space will be the envelope, and the orthogonal directional space will be the complement of the envelope. So recall that in standard analysis, X beta hat is the projection matrix times Y. So we do inference by projecting the data onto the Y space. So in the left panel, using the standard model, we just project our data onto Y space. In the right panel, using the envelope model, we project the data Y onto the envelope space to remove the immaterial part, and then project it onto the Y space. So again, when we see the standard model, the projection distributions are overlapped, so it requires more samples to detect the difference of the population means. However, when we use the envelope model in the right panel, the projection distributions are well separated, so the estimation will be more efficient. In the multivariate regression, we may have a subset of certain predictors we are interested in. We denote this by x1. So we can consider a partition x into two sets of predictors, x1 and x2, and we can write down our model with this equation. So we want to apply the envelope ideal to increase the efficiency gain for beta 1, and that is called the partial response envelope. So here we leave beta 2 as unconstrained parameters. So Su and Cook in 2011, they proposed the partial response envelope, and they assigned two conditions to construct the envelope. So for the fixed x2, the immaterial part of y, qy, does not depend on the value of x1 we are interested in. And another second condition is that given predictors, material part of y and immaterial part of y are not correlated, then we have the partial response envelope. We notice that this partial response envelope is contained in the full response envelope. So this will allow the partial response envelope to offer gains that may not be possible with the full response envelope. So far, I reviewed Y envelope, meaning that we reduce the dimension of the response vector. And envelope models have adopted to many other areas, and one example is a predictor envelope model. So now we want to reduce the dimension of the predictors. So in predictor envelope model, we reparameterize the model with the centered vector, and we assume that X is stochastic with mean mu X and covariance sigma X. And then we impose two conditions to construct the predictor envelope. So Cook and his colleagues in 2013 assumed that there is a subspace of p-dimensional real-valued space satisfying given the material part of X, immaterial part of X, QX does not provide any information for estimating beta. And material part of X and immaterial part of X are not correlated. Again, these two conditions can be rewritten by the parameters beta and sigma x. And recently, I developed the envelope-based partial least squares, shortened to EPPLS, or called partial predictor envelope model. So suppose that predictors X is partitioned into X1 and X2, where X1 is a vector of continuous predictors and X2 is a vector of categorical predictors. Then we could write down the standard model, and we further assume the linear relationship between X1 and X2. This is commonly seen in mediator or causal inference. So regressing X1 on X2, we have error term E, and this error E is assumed to be independent of the error in regressing Y on X. Again, we impose two conditions to construct the envelope models. Those two conditions are exactly the same as the conditions for the predictor envelope, except that I further condition by X2, the two conditions of the predictor envelope. Then we could define the smallest subspace of P1 dimensional space, and this is called the partial predictor envelope. So let's move to the new method called simultaneous partial envelope model. So in this work, we suppose that predictors X is partitioned into X1 and X2. X1 is the predictors we are interested in. And we further partition this X1 into X1C and X1D. X1C is a vector of continuous predictors we are interested, and X1D is a discrete or categorical predictors we are interested in. We assume that X1C is stochastic, while X1D and X2 are assumed to be non-stochastic. Then we could write down the standard model with the equation 5. In this work, our goal is to conduct the sufficient dimension reduction on both response and predictors of interest simultaneously, so that our model will provide a unified framework for the sufficient dimension reduction. Another goal is to improve the estimation of beta 1 and enhance the prediction. So our approach is to impose the partial predictor envelope and partial response envelope on the spanned space by beta 1C and spanned space by beta 1 transpose. We have two distributional assumptions, which is commonly done. So our errors epsilon follows the normal distribution, and we have the linear relationship between X1C and X1D. Then the model 5 with two distributional assumption equation 6 and 7 is called the simultaneous partial envelope model if we have two partial envelope structures with partial predictor envelope and partial response envelope. And according to a certain conditions, our model SIMP degenerate to the existing envelope model, such as a response envelope, predictor envelope, simultaneous envelope, partial response envelope, and partial predictor envelope. So this table shows the relationship and says that our method is the unified framework for the envelope models. So let's see the coordination form with the reparameterization. In the traditional envelope model, the challenging thing is to estimate the basis matrix of the envelope space. So in our work, we transform to the Euclidean space to estimate the basis matrix. So let's R and L be the orthogonal basis of the partial response envelope and partial predictor envelope. And R0, L0 be their completion. And let dx is the dimension of the partial predictor envelope. Then our basis of partial predictor envelope L is written as a submatrix L1 and L2. L1 is the upper dx rows of L, and we could assume it to be non-singular. And L2 is the remaining part of L. Then this is rewritten as a function of matrix A, C of A times L1, where A is L2 times L1 inverse. Since A depends on L only through the spanned space by basis L, so there is a one-to-one correspondence between A and the envelope space. So if C over A is the basis of the partial predictor envelope, then D of A having this form is a basis of the orthogonal complement of the partial predictor envelope. So we have the form for the basis L and L0. And as you could see, those bases are uniquely determined by the matrix A. Similarly, we could reparameterize R and R0, and they are determined by the matrix B, so that we have the coordinate form of the proposed method. So now beta 1c is replaced by L, eta c transpose, R transpose, and beta 1d is replaced by eta d transpose and R transpose. And sigma c given d and sigma y given x, they are represented as the omega 0, phi 0 with respect to their basis L, L0 or R and R0. We perform the Bayesian inference to estimate the parameters. We impose the prior distributions on parameters, such as improper flat prior on mean vector and matrix normal priors on beta 2, gamma, eta c, eta d, and the matrix for basis A and B. And we impose inverse Wishart priors on omega 0, phi, and phi 0. We developed the block Metropolis-within-Gibbs algorithm. So most of the parameters are generated from the full conditional distribution using the Gibbs sampler. And we sample the matrix A and B column-wisely by random walk Metropolis step. We established the two theoretical properties. The first theory is about the posterior property. Since we sampled from the posterior distribution, we need to ensure that the posterior distribution is integrable. So first theory shows that the posterior joint density is proper with respect to the Lebesgue measure. And the second theory is about the Harris ergodicity. This will guarantee that our sample will converge to the target posterior distribution. Because of the time limit, let me jump to the data application part. So as we see in the motivation study, I used ADNI data. ADNI is a multi-center study on the Alzheimer's disease launched in 2003. They collect the data for each participant in several aspects, including clinical, genetics, imaging, neuropsychological assessment, and so on. We want to study the genetic effects on brain volumes of cortical or subcortical structures, while we want to account for the effects of some other prognostic factors. So we take response as the brain volumes on 12 cortical or subcortical structures, and we take X1C as the 186 principal components of the synapse, X1D as the APOE gene. And X2 is the remaining prognostic factors such as gender, marital status, handedness, age, education, and so on. After data...
4 minutes left.
Thank you. So after data cleaning and quality control, we have approximately 500 samples. And of note, we originally have 693 snaps. However, this is larger than our sample size. So that's why we took the principal component analysis to reduce the dimension of the snaps. And we finally have 186 principal components, which is continuous. That's how we use X1C with the 186 principal components of the SNAPS data. We calculated the mean squared prediction error using 5-fold cross-validation based on 500 replication, and the proposed method lead to the smallest MSPE. We compared this with the partial predictor envelope, partial response envelope, and non-partial envelope and non-envelope models. We also investigated the association between predictors and responses. We used the credible interval whose confidence level is 0.95 with the Bonferroni correction. So the significance of any predictor is determined by the exclusion of zero value in the credible interval. The upper panel shows the indicator of the significance. We could see a few of genetic variants are significant for the 12 ROIs, and age and ICV have a significant effect on the brain volumes. And in the bottom panel, we draw the heat map to see the association. And we found that the pair of hemisphere shows the similar association for each genetic markers. And this is reasonable because of a strong bilateral association or correlation. We also found that the association for specific region of interest, such as inferior lateral ventricle, hippocampus, and amygdala, they have a relatively higher association. And this was verified in past research. So here is the summary. We propose a new unified envelope model by combining the partial predictor envelope and partial response envelope to offer a building block for the theoretical research of envelope model and provide an ideal choice for the practitioners. We showed that our method improves the estimation of efficiency and the prediction. And our method used the Bayesian framework, so it is more convenient to incorporate the prior information and to quantify the uncertainties through the posterior distribution. And here is the list of reference, and I especially thank to Korean International Statistics Society to support this session, and I appreciate my institute for generous startup. So thank you for your attention.
Thank you very much.